Hi, everybody. I'm going to give it a couple more seconds just to let everybody get logged on and get things under control. But I want to say hi and welcome to our AP Calculus session for today. My name is Leah. I see a lot of familiar names and faces in here. I'm so glad that you're back. If you have not yet joined us for one of these AP Calculus sessions, I'm Leah. I tutor a lot of ACT, SAT, and high school math courses at Prep Matters, and I teach high school math full-time during the school days. So a couple of just logistical things here for today's session. As a reminder, your microphones are not on. I cannot hear anything that you're saying. If you have questions for me, just like we have done in previous sessions, there's a Q&A button at the top of your screen. There is also now a chat function that you should see at the top of your screen. You can type messages in that chat function there, and they will come straight to me. And I will do my best to try to answer those questions as we're going. If I don't get to them, if I don't give you a detailed enough answer, I will try to answer a couple questions at the end of the session. You also can always send to me an email at classes@prepmatters.com. That email address will be on the bottom of my screen once I switch to the actual slides for this class as well. So that will always be an option there for you as well. Now, as another logistical reminder, I'm writing off my iPad, so I'm going to keep my camera off so that you are not just, sorry for a couple noises here, so that you are not just staring at the ceiling the entire time. I will bring it back and come back to talk to us all together at the end. So with that being said, let's go ahead and get started. All right, so this week we are going to move into AP Calculus Unit 5 on an AP syllabus. This is most likely what you would have covered in November or December, right before the actual school year let out for winter break during the regular year. This is the analytical approach to derivatives. So how functions and their derivatives connect graphically and what that means for calculus, what that means for curve sketching, what that means for different application problems, all of this material. It's much more theory-based than what we have talked about in some of the other sections. It's a lot less application. So we are going to look pretty briefly at these three theorems here: mean value, intermediate, and extreme value, just kind of in conceptual terms, what we're looking at here. And then these next couple of bullet points, using the first and second derivative tests, determining increasing and decreasing intervals, determining concavity, and sketching graphs of functions and their derivatives. This is kind of all one giant connected piece. So I'm going to talk about this all together as one thing. And then at the end, we're going to do an optimization problem. So just like in the last session, we ended with a related rates problem, we're going to end this one with an optimization problem so that we can do some comparisons and contrasting of how to do those different types of problems. But before we do any of that, I would like to start with a related rates problem. If you viewed the session for last week, whether you viewed it live or as a recording, this is where we left off. We stopped with this related rates problem. And I want to pick up here today. Again, just like I just said, we're going to end today with an optimization problem. So starting with this related rates problem is going to give us a really good comparison between two different types of derivative-based word problems. So let's look at this problem here. In this problem, we have person A. Person A is running west at a pace of 5 miles per hour. So person A is going this way. Person B is running north at a pace of 6 miles per hour. So person B is running north. Both are headed for an intersection of two roads. At what rate are the runners approaching each other when person A is 1.2 miles from the intersection and person B is 1.6 miles from the intersection? So just like we talked about in the last session, when we are doing related rates problem, we always want to sketch things out. Related rates problems are pretty hard to figure out how to work if we're just kind of staring at information in word form. So if we sketch this out, I'm going to zoom in here and then I'll bring this back so that we can talk about it out all together. We have this person A running west and person B running north. And they are going to meet at an intersection. We are trying to figure out the distance between person A and person B and how that's changing. When we sketch all of this together, we have this situation, which looks like a nice, beautiful right triangle. And we have three variables. I'm going to call them A, person A, B for person B, and then C, I'll make the hypotenuse of a triangle. It doesn't matter what your variables are, X, Y, Z, A, B, C, whatever you want to label them, that's fine. This is another great reason to sketch a diagram. However you sketch a diagram and label your kind of pieces of your diagram, that will flow through your math, and that will always make sure that your AP reader knows exactly what you're talking about. So I have these three variables, A, B, and C. We are going to lock into a specific point in time where we know what A is and we know what B is, and then therefore we will know what C is, but we also know that they're changing. So A is changing as time changes, B is changing as time changes, and C is changing as time changes. So all three of these variables, all three of these lengths of the triangle, if you will, are changing with time. So we know that the rate of change of A is 5 miles per hour. I'm going to make sure my units get into the end. If you carry them through your work, that's awesome. If you don't, make sure that they are there at the very end. And our rate of change of B is 6. So 6 miles per hour, 5 miles per hour. Now, here's the tricky part for this problem, and this is why I love looking at this problem. Both of these rates of change are negative. So our rate of change for A is -5 and our rate of change of B is -5, which is not at all clear or maybe intuitive from the actual setup of the question. So since the actual distance of A, so let's say person A right now is right here. We're aiming for right here. Since the actual distance of A and the actual distance of B are decreasing, those lengths, those sides of the triangles are getting smaller, these rates of change are actually negative. The position is decreasing. The position of person A, we're getting closer and closer and closer to, for instance, this origin point. If you relate this to physics, that would mean that your velocity is negative. You're approaching the origin. So that makes your rates of change negative. Now, we want to evaluate all of this at a specific value of A and B. We know that A, for instance, is going to be 1.2 and B is going to be 1.6. That means that we can do a nice, pretty Pythagorean theorem on C or 4C, or recognize this manipulation of a 3, 4, 5 triangle and realize that at that point of time, at that point in time, C will be equal to 2. So again, when we're doing related rates problems, we end up with a specific point in time that we are using for our variable information for this A, B, and C here. When we're doing those geometry type problems, we're looking at a specific point in time where we know the radius, we know the height, we know whatever measurements we're looking at. But A, B, and C are not always these values. R and H are not always those values, whatever we're looking at. They are changing. That's why we have these rates of change. Specific point in time, but rates of change in general. So then this is a nice, relatively simple related rates type problem from a related rate standpoint, because I have 6 pieces of information or 6 variables and I know 5 of them. This is what I'm actually looking for. And that's the setup for related rates problems. That's what we talked through in the last session. Figure out how all of your variables relate to each other. Sketching a diagram is really helpful. Figure out what those variable numbers actually are at the point in time where we are going to look. And then figure out what equation we can write to relate them. In this case, this is a right triangle. Pythagorean theorem works beautifully here. A squared plus B squared equals C squared. Whatever these variables are up here, we have to try to figure out how to relate them. That's the goal of this part. A lot of times this uses geometry formulas when we're in a triangle setting. Hopefully that Pythagorean theorem will work really well here. And then once we have our equation, we are differentiating with respect to time, always differentiating with respect to time for a related rates problem, which means that we are going to use implicit differentiation. Implicitly differentiating this entire thing would give us an equation that looks like this. Once we differentiate everything with respect to time, we can throw in all of the variables that we know. In this particular case, I know A, I know the rate of change of A, I know B, I know the rate of change of B, I know C, and I'm trying to figure out the rate of change of C. From this point on, it's throwing numbers into this equation, substituting for everything we possibly can, solving for this dC over dt, or this rate of change of C, and then answering the question. Once we do that, once we throw all of this into a calculator, we end up with this information right here. The rate of change of C is negative 7.8 miles per hour, which would mean, let me zoom back out to the question for you, which would mean that person A and person B, these two runners, are approaching each other at a rate of 7.8 miles per hour. The rate of change of C of this distance right here is negative, but in the wording of the question, we're already talking about it being negative. We already know that it is decreasing. We already know that this distance between A and B is getting smaller. So we would say that the runners are approaching each other at a rate of 7.8 miles per hour. All right, now let's jump into all of the new content for this particular session, starting with these 3 theorems. Again, since the AP exam isn't necessarily going to be a memorization game anymore, I'm not going to draw out the explicit theorems with their proper notation and technicalities here. You can find that in your notes from class from again, probably November-ish or December-ish, or in a textbook, but I do want to quickly look at what these theorems actually mean. So starting with the mean value theorem. Remember that the word mean in a nice algebra world, or SAT or ACT, is synonymous with average. So mean value theorem looks like this. This is a theorem that relates the slope of a secant line between 2 points to the slope of a tangent line. So slope of a secant line, slope of a tangent line, things that we have talked about in the very first review session for calculus, that content, that slope of a secant line has to do with your average rate of change, slope of a tangent line has to do with your instantaneous rate of change. And that's exactly what this is talking about. Specifically, this theorem says that there exists a point between 2 points A and B, we'll just call it C, most textbooks call it C, where the derivative at C, or the slope of the tangent line at C, equals the average rate of change, or the slope of the secant line, between A and B. So in graphical terms, that looks like this. Let's say we have a function. Let's let that function look like this. And I'm going to add point A right here and point B right here. So then if I do that, I would have f of A and f of B looking like this. Now, this theorem says that between A and B, so somewhere along this point of the function, let me see if I can take away all the rest. So between A and B, there exists some point C such that the slope of the tangent line at C is equal to the slope of the secant line between A and B. So our secant line between A and B would look like this. And then we would know that between A and B, somewhere, I'm going to say approximately right here, we would have a tangent line that has the same slope. So slope of this secant line is equal to the slope of the tangent line at C, which would mean that these two lines are parallel. That's what the mean value theorem is saying. Somewhere between A and B, there exists a point C such that the slope of the tangent line at C is equal to the slope of the secant line between A and B. Okay, intermediate value theorem. Let's look at this one. This one is a little bit less calculus heavy than the mean value theorem. It does not pull any knowledge of derivatives at all. This one is saying that if we have 2 points on a function, again, I'm just going to call them A and B, the theorem says that there is an x value in between A and B that has a function value between f of A and f of B. So graphically, that looks like this. Say we have a function. Apparently every function that I sketch looks relatively similar. Let's say I have point A right here and point B right here. So then I have f of A and f of B. And we are going to just concentrate on the part of the function that is between A and B. So ignoring everything else. And the intermediate value theorem is saying that there is some point, let's see if I can use a color that I have not yet touched. There is some point between A and B that has a function value between f of A and f of B. So whatever that function value is, let's say it's n, there has to be a point between A and B. That was some pretty poor sketching. Let me fix that. There has to be a point between A and B that actually has that function value, which ideally is exactly what intermediate value theorem should sound like. These names are pretty great for figuring out what these theorems actually mean. And then the last one here, intermediate value, no, not intermediate value theorem, sorry, extreme value theorem. So extreme value theorem, even less calculus heavy than the intermediate value theorem. The extreme value theorem tells us that if we're looking at a function between A and B, between x values A and B, then the function has an absolute maximum and an absolute minimum somewhere on that interval. So basically, if we restrict the interval that we're looking at, we have to see extreme values. We have to see an absolute minimum and we have to see an absolute maximum. Graphically, that would look like this. I'm going to try to draw a different looking function this time. So maybe we start this way. So if we start with a function that looks like this, I pick a value of A and I pick a value of B so that I'm looking between 2 points. And then I say I'm only going to look between those 2 points, A and B. So I'm only going to look at this part of the function. Well, when I'm looking at just this part of the function between x values A and B, I have to see an absolute minimum, which in this case would be right here. And I have to see an absolute maximum, which would be something in this general range. There has to be an absolute minimum. There has to be an absolute maximum when we're looking at a restricted interval. Now, hopefully, this is kind of ringing or some kind of light bulbs are going off with this part right here. There's a big key to everything that I just said. Everything that I talked about is only true if, yes, and this is exactly the question that's coming in right now, exactly what I am about to talk about. Yes, this is only true. Everything that I just talked about is only true if the function in question is continuous between A and B. So if the function is not continuous between A and B, we can't make any of the claims that we just made, which should seem fairly obvious. If I know there's not a smooth continuous pattern between A and B, then I can't really make any claims about what's possibly going on there. There could be a jump discontinuity factor. There could be some kind of vertical asymptote. There could be a lot of information that we still need to know in order to make any claims like this. So everything that I just talked about here, everything with the mean value theorem, intermediate value theorem, and extreme value theorem, all require our function to be continuous between A and B. Now, the mean value theorem, since it is relying on the slope of a tangent line, would also require that the function be differentiable between A and B. So that's the big key that I want you to think about or remember in these types of questions when thinking through these theorems. They're relatively easy to use, but we can only use them if we know the function is continuous between A and B in all three situations. And then for the mean value theorem, that we also know the function is differentiable between A and B. Okay, so let's look at what this actually looks like in a question. Question number 1 today is a piece of a free response question to show you just kind of what the use of one of these theorems could look like in a question. This is the first part of one of the questions from 2018. So for the first part here, part A, we're going to do just a little bit of old derivative work. And then part B, this second part, we'll use one of the theorems that we just talked about. So this question stem looks like this. The height of a tree at time t is given by a twice differentiable function, h, where h of t is measured in meters and t is in years. Selected values of h of t are given in the table above. Now, this is always really great wording to read when we're looking at things. We like to read this word differentiable because then we know that this function is also continuous. So there are our conditions right there. We know that this function is continuous because it is differentiable on the interval that we're given. We remember that a function has to be continuous in order to be differentiable. So we already know our conditions are checked. So for the first part here, we want to estimate the derivative at 6 and then interpret the meaning and context of the problem. This is nothing new from this particular session. So the derivative at h is the slope of the tangent line to h at t equals 6. We don't have a graph, we don't have an equation, we don't have any way to find the exact slope of the tangent line. So in this case, we will have to do an approximation using the smallest or shortest, whatever your best wording is there, your shortest secant line that we possibly can. So in this case, I'll use the slope of the secant line between, what do we want at 6? We'll use the slope of the secant line between 5 and 7. That will give us an approximation for the slope of the tangent line or the derivative at 6. So that will look like this. So h prime of 6 is approximately, it is not equal to, it is approximately equal to the slope of the tangent line, not tangent line, secant line, the slope of the secant line between 7 and 5. So a nice pretty slope formula right there. That will give us approximately 11 minus 6, so 5 over 2. That gives us a derivative at 6, a slope of a tangent line at 6 of approximately 5 over 2. And that 5 over 2, that will have units, that 5 over 2 will be meters per year. We are in meters per year, exactly what that actually represents mathematically. And then we can always do that interpretation using those words rate of change. So this slope of the tangent line means that the rate of change of the height of the tree at time 6 is approximately 5/2 meters per year. 5/2, 2.5, whatever you want to show that as. So the rate of change of the height of the tree at time 6 is approximately 5/2 meters per year. The second part is the new part from today's session. Explain why there must be at least one time t for t between 2 and 10 such that h prime of t equals 2. This is a pretty common question setup or question stem for the use of either the intermediate value theorem or the mean value theorem. This explain why there must be some time between other times or x value between other x values, whatever your context is, such that something. Now in this particular case, that such that is involving a derivative. That's going to clue us into the mean value theorem instead of the intermediate value theorem or extreme value theorem. So this h prime of t equals 2 means that somewhere we are going to need to find a slope of a secant line between 2 points that actually equals 2. So looking at this table hopefully gives us a nice, almost obvious set of 2 points that have a secant line between them, or slope of a secant line between them that's equal to 2. Usually this should be pretty easy to just kind of look at and see. I know that's a terrible kind of mathematical process right there, but hopefully it is kind of easy to see based on the table. If not, it's not ridiculously challenging algebra to run through. It kind of goes pretty quickly if we just want to test, okay, what's the slope of the secant line between 2 and 10? What's the slope of the secant line between 3 and 10? What's the slope of the secant line between 3 and 7? And so on and so on. That algebra is not long. It should not take forever if it's not easy to see right away. In this case, hopefully it is. Between these points here, between 3 and 5, we would have a slope of 2 if we looked at the slope of the secant line here, 6 minus 2 over 5 minus 3. So to actually formally write this answer, this is the fun part. To actually formally write this up, let's see what I can do in the space that I've left myself. We need to show that the mean value theorem can actually work, that it actually applies. And this is the part that's usually forgotten. This is why I explicitly want to look at this question right here. So we know that h of t is differentiable. The question tells us that. We're going to zero in on the interval between 3 and 5. So h of t is differentiable. I'm going to slightly abbreviate this one here. Is differentiable between 3 and 5. And you can write this a lot of different ways. We can say h of t is differentiable on the interval 3, 5. We can say between 3 and 5. We can use this kind of notation that the question already used. Not picky necessarily on that. We just need to make sure that we're clear about what we're saying and make sure that we have all of the parts of the question there. So h of t is differentiable between 3 and 5. Therefore, h of t is continuous between 3 and 5. Again, differentiability implies continuity, not the other way around, but if we know that a function is differentiable, we know that it's continuous. Then we can look at this slope of the actual secant line here, and we can say that h of 5 minus h of 3 over 5 minus 3 equals 2. So there are all of your pieces of the mean value theorem. Condition, condition, actual math. Once we have all of that, then we can say, because of all of that, therefore, and I'm not going to write this one out, but therefore, there exists a value of t somewhere between 3 and 5 for which h prime of t is equal to 2. So therefore, there exists all of that. There exists a value of t between 3 and 5 for which h prime of t equals 2. Again, the math is not incredibly awful, but we do want to make sure that we check those conditions. Okay, now we're going to get into a lot of great concepts. Again, please keep making use of that Q&A feature for questions or the chat feature, either one, and I will keep trying to get to them as we go on. Okay, so now we're going to move away from specific questions for a few minutes and talk about the actual concepts that connect the graphs of a function and its derivative, and a function and its second derivative. So I'm going to use these 3 functions here to review some ideas. So I have a cubic function to start, and then its derivative, which is a quadratic function, and then its second derivative, which is a linear function. And I'm going to scribble all over these, so let's see what we can do. Okay, so to start, I want to just look at a function and its derivative. So if we look at this function f, this cubic function, we can start approximating its derivative by thinking through the slopes of the tangent lines at various points. So assuming that I didn't necessarily have this algebra right here, and I couldn't really quickly go to an algebraic derivative, if we go all the way back to our concepts, we could theoretically build the graph of a derivative based on the graph of the function. So if I start looking at my function from as far left as I can, and I just start kind kind of thinking about the slopes of the tangent lines, as my function is increasing, I have slopes of tangent lines that are positive and getting closer and closer to 0 until all of a sudden they would become 0. Then if I keep sketching little tangent lines, my tangent line slopes are negative as my function is decreasing until I have a tangent line with a slope of 0. And then I would have slopes of tangent lines that are positive as my function continues to increase again. So if we compare that to the actual derivative, where my function is increasing, let me fix that, sorry. Where my function is increasing, my derivative is positive. The slopes of all of those tangent lines at every single point on this increasing interval are all positive. Then when my function is decreasing, my derivative is negative. The slope of every single tangent line at every single point on this decreasing interval is negative. And then as my function increases again, my slopes of every single tangent line at every single point on that increasing interval are all positive again. When we get to a minimum or a maximum of a function, so maximum here as our function switches from increasing to decreasing, we're going to have a derivative that's equal to 0. And where I have a minimum on my function switches from decreasing to increasing, my derivative will equal 0. This is the first really important connection between the graph of a function and its derivative. When a function is increasing, the derivative is positive. When a function is decreasing, its derivative is negative. When a function has a maximum or a minimum value, its derivative is 0. And this is true, this is a really big key here, this is true for any set of functions where one is a derivative of the other. So for instance, if I relabel this entire thing, and I say that instead of this being my original function, this is actually my third derivative, and then this would be, this would be my fourth derivative. Everything that I just said is still exactly true. It doesn't matter that I'm no longer talking about a function explicitly labeled as f of x and a derivative explicitly labeled as f prime of x. This is true of all functions and that function's first derivative, regardless of where in the giant chain of derivatives the two functions fall. So again, everything that I just said applies to any function and its first derivative. Where a function is increasing, its derivative is positive. Where a function is decreasing, its derivative is negative. And then we can take that backwards as well, of course. Where a function's derivative is positive, the function is increasing. Where a first derivative is negative, the function is decreasing. We also have a connection. Let's actually change this first. Okay, so we also have a connection between a function and its second derivative. So where a function, let's move this over. So where a function is concave up, so concave up, its second derivative is positive. Where a function is concave down, its second derivative is negative. Where a function is changing concavity, we call this a point of inflection, the second derivative is equal to 0. And in the same way as before, this relationship applies to any function and the second derivative of that function. So if we had a giant derivative chain, for instance, the positive and negative intervals of the 9th derivative would tell us about the concavity of the 7th derivative, two functions above it. The positive and negative intervals of the 8th derivative would tell us about the increasing and decreasing intervals of the 7th derivative, one function above it. connection between a function and its derivative, a function and its second derivative. Okay, so let's take that a little bit further. So I want to formalize that just a little bit more. I'm not going to really focus on the actual idea of curve sketching as you may have done it in the actual AP curriculum over the school year. The part that gives you a function and then really just says, sketch this function using all of your knowledge of derivatives, because this becomes a little bit less of a good way to test your knowledge of these relationships once you have a calculator in your hand. But I do want to summarize these ideas before we really jump into an actual AP problem. So let's formalize all of this information about a function. And its derivative. And its second derivative. And again, I'm labeling this as f of x, f prime of x, f double prime of x. Does not have to be labeled that way. Any function, its derivative, its second derivative. So we know that when a derivative is positive, the function, its function, is increasing. And we know that when a derivative is not decreasing, is negative, its function is decreasing. Okay, why can I not write? There we go. Its function is decreasing. And we also know that when a derivative is equal to 0, this part is going to be a super important part, then we have a potential maximum or minimum. I don't want to explicitly say that we have a maximum or minimum, and I'm going to show you this graphically in a minute, but we have a potential maximum or minimum. Derivative is positive, function is increasing. Derivative is negative, function is decreasing. Derivative is 0, then we could have a maximum or minimum. And I can just do this entire piece again. Not necessarily that. This entire thing again for the first derivative and the second derivative. Because I also know that when, for instance, the second derivative is positive, the first derivative is increasing. And when the second derivative is negative, the first derivative is decreasing. And I can just keep doing this forever and ever and ever if I really wanted to draw this out. If we had a third and a fourth and a fifth and so on derivatives listed, this piece right here could just keep going down. Now we also know that when a second derivative is positive, then the function, its function 2 functions up, is concave up. When a second derivative is negative, then the function, its function 2 functions up, is concave down, which also now gives us more information. Now we have this relationship that we can see when a derivative is increasing, its function is concave up. When a derivative is decreasing, its function is concave down. That relationship is used a lot less because it's just, I guess, less maybe intuitive, but it is a relationship that we can pull off of this chart here. And we also have, that is not what I wanted to do. We also have this idea that when our second derivative is equal to 0, our function is changing concavity, and we call that a point of inflection. So this chart right here, these ideas are kind of the backbone of all of the curve sketching, relationship between graph type for your response questions on an AP exam. They're very commonly tested topics. These questions appear over and over and over because they are incredibly theoretical. So this is something that, right along with that idea that the slope of a tangent line is equal to the instantaneous rate of change equal to the derivative, slope of a secant line is equal to an average rate of change. Just like those ideas, this chart, graphical display of ideas You want to get this into your brain to kind of be the backbone of all of our questions as well. All right, so now we're into a big AP question, and this is modeled off of a question from the 2016 exam. It's a slight manipulation of the 2016 exam, question number 3. So I say slightly modified because this AP question in its entirety would require a little bit of integration knowledge that I'm going to leave out of this today. I'll throw that back in our next session when I do talk about integration and all of the different theories and techniques and everything there. So we're just going to focus on the graphical display derivative relationship ideas today. So most important thing to pick out of this question before we even really dive into the math here, when we are given a graph, always stop and make sure you label it and actually internalize which function it is. So the figure above shows the graph of a piecewise linear function f prime of x. So we are already looking at the first derivative of a function. And all of our question pieces, A, B, and C, all ask for information about the function. That is so important to note. Everything about your answers to all 3 of these questions will completely change if you think that you're looking at something else. If we take the graph as the function, for instance, and then start answering questions about the derivative, or if we think that we're looking at a second derivative when we're looking at a first derivative, whatever it is. So this graph here is, what did I just say, is a derivative. We already know we're looking at the derivative. Most important thing to note. Now I'm going to step through all of these pieces on different slides so that I can write in a little bit more space. But just before we do that, as a quick kind of judge of what we're doing here, we are going to be looking at relative minimums and maximums, points of inflections, and then absolute minimum, absolute maximum. So we're looking for those points of inflections, those points where the second derivative is equal to 0, and those maximums and minimums, those points where the first derivative is equal to 0. So this is going to be a giant manipulation, of all of this. All right, so let's look at just the first part. I moved the graph down to the bottom so that we can write in a little bit larger of a fashion here. So let's look at what we know. So first part, does f have a relative minimum, relative maximum, or neither at x equals 10? Justify your answer. That justify your answer part is generally included in these questions. Make sure you're actually showing or explaining why you're going to answer what you're going to answer. AP is not going to be super thrilled about just seeing relative minimum, the end, or relative maximum, the end. The reasoning is the important part here. So we know that when our derivative is negative, again, we're looking at the derivative here. This is a graph of the actual derivative. And I know that for everything here, for every single x value where my derivative is negative, my function is decreasing. I always like to label this on my actual graph so that I can easily relate this to the question. You don't have to, of course, it just might make things a little bit easier. And I know where my derivative is positive, my function is increasing. So if we look at this x equals 10 x value right here, the derivative is equal to 0 at x equals 10. But to the left of the to the left of x equals 10, this derivative is negative. So the function is decreasing. To the right of x equals 10, the derivative is still negative. So the function is still decreasing. The function does not change from increasing to decreasing or decreasing to increasing at x equals 10 because the first derivative does not change from positive to negative or negative to positive. That means that while we do have a horizontal tangent line, we do have a derivative equal to 0 at x equals 10, we do not have a minimum or maximum. We do not have a minimum or maximum because we are not changing from increasing to decreasing or decreasing to increasing. This function is decreasing, has a horizontal tangent, decreasing again. So it could look something like this, where it's decreasing, horizontal tangent, decreasing. That does not create an extreme value. So to write up an answer like that, it doesn't have to be long and complicated, but to write up an answer like that, we could say f has neither a relative minimum or a relative maximum at x equals 10 because f is strictly decreasing on the interval from, we can just kind of pick something around that, on the interval from 8 to 12. This is the exact same question so far. I just want to show you some slight wording changes. In contrast to the question that we just answered, this part right here, we can see questions that look like this as well. It's the exact same math that we're looking at, the exact same concepts that we're being asked about. It's just in a little bit of a different phrasing situation. So find the x coordinate of each point at which the graph of f has a horizontal tangent line. So everywhere where our derivative is equal to 0. For each point, determine whether f has a relative minimum, relative maximum, or neither a minimum nor a maximum at that point. Justify your answers. This is exactly what we just did. We would just have to do it for every point where we have a derivative equal to 0 and not just x equals 10. We would just have to do more work. But those are the two types of wording, two types of phrasings that you'll see for a relative extrema question from a graphical standpoint. All right, second part. Does the graph of f have a point of inflection at x equals 4? So remember that a point of inflection means that concavity of the function changes. Also remember, we're not looking at the function. So concavity of the function changes. So let's start mapping that out. So concavity changes, that means that the derivative, or the second derivative at, what value are we looking at? 4. At 4 needs to equal 0. That's how our concavity will change. That means that we are going to have a maximum or a minimum, or we could have a maximum and minimum of our derivative at x equals 4. If concavity of the function is changing, then the sign of the second derivative is changing. If the sign of the second derivative is changing, then the first derivative will change from increasing to decreasing or decreasing to increasing. And this does happen right here at x equals 4. Our first derivative is increasing, which would make the second derivative positive. And then it is decreasing, which would make the second derivative negative. The second derivative changes from positive to negative at x equals 4. Specifically at x equals 4, the second derivative would be equal to 0. And that would mean that we do have a point of inflection. Our function does change concavity at x equals 4. So just like for the first part, I want to show you a slight variation of wording for this type of question as well. So this is what we just did. We also can have this wording right here. Find all values of x for which the graph of f has a point of inflection and explain your reasoning. So same type of idea. We're just not zeroed into one specific point. We have to look for all of the points. We need to figure out all of the points where our, in this case, first derivative changes from increasing to decreasing or decreasing to increasing, which would mean that our second derivative would equal 0. And then last stem here, and we can't actually do this entire question until we bring integration into the mix, but I want to show you an important piece of this part. So last part of this question stem, part C, find the absolute minimum value and the absolute maximum value of f on the given interval. Justify your answers. So this time we're looking for absolute, the overall minimum, the overall maximum value. We also want to know the actual values. And I want to point that out because that when we're being asked for the actual values, we want the y values, or the f of x, whatever variables we're looking at here, the f of x value, not the x value. That's a common point of confusion on these type of questions. Even when the math is done beautifully, answers are given as x equals something, x equals something. When we're being asked for the actual absolute minimum or maximum value, that's the function value. So in this case, this means that we need to find all potential maximums and minimums, whether they're going to be relative, absolute, whatever, all the potential maximums and minimums, including the endpoints. And that's the part that's generally left off of a question like this. Since we have a closed interval, we know that this function is stopping, or what we're looking at is only between x equals -4 and -12. We need to evaluate endpoints as well. So we know that we are going to have some kind of maximum where the function is going to change from increasing to decreasing. So the first derivative, what we're looking at, would change from positive to negative. So we have some kind of maximum at x equals 6. We don't necessarily know if it's absolute or relative, but we have some kind of maximum at x equals 6. We also know that we're going to have a minimum where our function changes from decreasing to increasing. So our derivative goes from negative to positive. So we have a potential absolute minimum at x equals -2. So some kind of max, some kind of min. Again, I do not know if they're absolute, or global is also wording that you may have been using for that. I don't know that they're absolute, but I know I have some kind of max and min here. Like we already talked about, we don't have a maximum or minimum at 10 because our function is decreasing on both sides. And we also don't have a maximum or minimum at 2 because our function is increasing on both sides of 2. Those are just horizontal tangent lines that do not relate to extrema. So what we would actually do, we're kind of at a standstill for this point of the question here till we throw integration in, but what we would actually do with this is look at x equals 6, x equals -2, and the two endpoints, x equals -4 and x equals positive 12. That's a terrible looking 12. X equals positive 12. And we would evaluate all of the function values for those 4 points. So we would find f of 6, f of -2, f of -4, and f of 12. And that part is the part that would require integration. Once we do that, we would be able to compare them, and we would easily just see the maximum and the maximum and the minimum. So I'm going to stop it there until we talk about integration next in our next session, but that's how we would continue this. Okay, last question. So the last part here is going to be the contextual application of all of this information, which we generally see in an optimization problem. So just like in the last session when we talked about units 3 and 4 of the AP curriculum, our application of the implicit differentiation and everything that we were talking about was a related rates problem. We see the application of all of these graphical connections and theories as an optimization problem. We often see these take the form of geometry problems, but they really can be any type of problem where we are given a function with the goal of either maximizing or minimizing that function. So that's what the actual optimization point is referring to. So in terms of what we just looked at, finding the maximum or the minimum value of a function is finding a point or the point on the function where its derivative equals 0. So let's look at this particular problem. So a cylindrical can is to be made to hold 1,000 cubic centimeters or 1 liter of water. Find the dimensions that will minimize the cost of metal needed to manufacture the can. So to start this problem, let's see what we actually have. In this case, we have a cylindrical can. Let's see what I can do here. I'm going to pretend this is a nice, beautiful cylindrical can. We have a cylindrical can. That can is going to have the dimensions of a radius and a height, and we have no idea what either of those things are. We want to minimize, so there's your optimization word. Again, we want to minimize the cost of metal needed to manufacture the can. Well, the metal, the actual cost that we're looking at, that's going to be related to the area. So I want my area of this can to be as small as possible. I want the minimum area. What that would look like, and in terms of everything that we just did, if I have a graph for an area function based on changing my radius and my height, if I have a graph of what that area curve would look like, I want to find its minimum value. I want the absolute minimum point on the area curve. Now, I just said a couple of things in that sentence that are going to need a lot of work based on how we set up our variables, but I'll get to that one in a second. So since we just talked about minimizing area, we need an area formula. Area of this can here, I'm going to call it capital A, generally what we would use for area. Area of a can is going to, or a cylindrical can is going to be 2 circles. So area of 1 circle twice, plus the area of the unrolled side of the can, whatever you want to actually call that there. When we do that, we are going to have a rectangle that has a base of a circumference of the circle, so 2 pi r, and a height of the actual height. So there's my area formula. Now, notice that this is an equation in terms of 2 variables. This is an equation in terms of r and of h, and we do not at all want that for an optimization problem. This area is not changing with respect to time, like in a related rates problem, where we can implicitly differentiate everything with respect to time. The area is changing with respect to these actual, I just erased that, sorry. With respect to these actual variables. So we need to differentiate with respect to those variables. Now, in order to do that well, in order to do that easily in the way that makes the most sense for this problem, our first goal is going to be to relate these 2 variables together somehow so that we can write one in terms of the other. In most optimization problems, this is why you're given a piece of seemingly unrelated, but kind of important sounding information. And in this case, it's this volume information. We want this can to hold 1,000 cubic centimeters of water. Great, that doesn't really seem like it is going to necessarily apply to the optimization of the area. And it's not necessarily, it's just going to give us a relationship between R and H. So I know that, I'm gonna go off to the side and write a different formula. So I know that the volume of a cylinder is the area of the base, so pi r squared, times the height, pi r squared height. Again, don't focus too much on these geometry formulas. You'll be able to create a formula sheet theoretically for yourself here. So volume is equal to pi r squared h. I also know what the volume is, and I know that volume is never going to change. The volume has to be 1,000 cubic centimeters. So I have this equation here, and I can use this equation to either write r in terms of h or h in terms of r. And I'm going to solve this for h because it seems like in this equation, it's going to be way easier to just substitute this h right here for a different expression. So if I do that, I'm going to have 1,000 divided by pi r squared equals h. So I created and used that secondary equation in order to go rewrite my first equation, my primary equation, in terms of only one variable. So now I can say that a equals 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And I'm just going to clean that up for a minute. I'm not going to do any crazy math yet. So 2 pi r squared plus 2,000 over r, that cleans up beautifully. So now I have this area formula right here. Area equals 2 pi r squared plus 2,000 over r. I created an equation that is in terms of only one variable. This is just like having this situation with no context and doing everything that we just did on the slides before. Since we have context, we generally don't write our functions in terms of f of x, but there's no reason that we can't. I'm just going to put those letters back If it makes you happier to do your entire problem in terms of f and x, go for it. As long as you label your diagrams to correspond with that. So now I'm going to differentiate a with respect to r. So the derivative of a with respect to r, just like doing a derivative in this form right here, if we had our function written as a of r and then a prime of r. When we do that, we're going to get 4 pi r minus 2000 over r squared. If it makes it easier to think through this part right here, makes it easier to think through this part, instead of writing it as a quotient, you can write it with a negative exponent like this. I tend to do that for quick differentiation. Up to you, up to what you're comfortable with. So I have my derivative. Once I have my derivative, my goal is going to be to figure out where that derivative equals 0. So I'm going to take this off to the side now over here so that we have a little bit more room. So our goal is to figure out where this equals 0. And in order to do that, of course, we can turn to technology at this point, or we can actually do the algebra. I'm going to go through the algebra because it's a good exercise here. So turning this into one giant fraction with a common denominator would give us this expression. If I want to know where this expression is equal to 0, I need to set the numerator equal to 0. The denominator can't be equal to 0. I need to set that numerator equal to 0, and then really I am just going to solve this equation. So 2000 over 4 pi equals r cubed, which would mean that the cube root of 2000 over 4 pi equals r. If we simplify that even more, just 500 over pi. Cube root of 500 over pi equals r. So that is giving us our r value where the derivative is equal to 0. Now, mathematically, you did the hard part. We figured out where, theoretically, we figured out where this area curve will have its minimum. In order to properly do an optimization problem, we should verify that. We should verify that this point is actually a minimum on our area curve and not accidentally a maximum or just some kind of other value. So in order to do that, there are two options. We can either do a first derivative test or a second derivative test. I'm going to hopefully run through both of those pretty quickly for you. If we were going to do a first derivative test, we can look and kind of see what the first derivative will look like, if it will be positive or negative on either side of that actual r value that we just found. So my area function is, or it can't be necessarily, less than 0 until we get into those nice fun integration pieces. So my area is going to go from 0 to, let's just say, infinity. And we have this point here, this nice messy number, which is probably some single digit number. Again, you'll have a calculator. Your crazy numbers and all of that super hard math is not going to be something to really forget about or focus on. But if we're looking at this, I want to know if this is a minimum, which means that my function, my area function, is going to need to be decreasing and then increasing, which is going to mean derivative-wise, first derivative test, derivative, that my derivative needs to be negative and then it needs to be positive. And we can test values to check that pretty quickly. So if we test a value in this interval, so something between 0 and the cube root of 500 over pi, let's just pick 1 to make that nice and easy. If we take the value of 1, r equals 1, and throw that into our derivative, which I have moved all over the place here, we throw that into our derivative, which is here. That's going to give us a negative derivative. It's going to give us 4 pi minus 2000. That is a negative number. So I have a negative derivative. In this interval, no, I'm not talking about functions. A, the derivative of A with respect to R is negative. And if I take a number that's very large, some number in this interval over here, and I substitute that into my derivative equation, I will hopefully see that my derivative is positive. Let's pick an obnoxiously large number just to see this really easily. So say something like 1,000, 100,000, whatever it might be. When we look at our derivative, when we plug in or we substitute in a really large number, this denominator is growing incredibly quickly. This entire piece of the fraction right here is going to get really close to 0. This will be positive. So I'm going to have a positive number minus something incredibly small. That will give me a positive derivative. So in this case, your derivative with respect to A, nope, just getting your derivative with respect to R, is going to be greater than 0. That will verify that our point that we just found, this cube root of 500 over pi, actually is the minimum. That's a key for an optimization problem, and that's the part that's generally left off. We want to find our x value, which is an r value in this particular case, where the derivative actually is 0, but we want to verify that it is a minimum if we're supposed to be minimizing a function, and a maximum if we're supposed to be maximizing a function. What we would do in order to do that is create this is called a sign chart, create a sign chart like we just did. Test a value to the left of our found value, see if our derivative is positive or negative. Test a value to the right of our found value, figure out if our derivative is positive or negative. We could also do a second derivative test. What that means is we could find the second derivative of our function, going back to our first derivative, find the second derivative of the function, and then evaluate that second derivative at our value that we found, at this value. If we evaluate the second derivative at this value and our second derivative is positive, we know that our function is concave up at that value. That would mean we have a minimum. If we evaluate our second derivative at this particular value and our second derivative is negative, then our function at that value would be concave down, which would mean that we are looking at a minimum. So that is two different ways to verify whether we're looking at a maximum or a minimum point. And that is all for this particular session. So we just talked through, very briefly, we talked through some theorems, and then a lot of connecting theories between graphs of derivatives, first derivatives, and both first derivatives and second derivatives, and how that relates to the graph of a function. And then one quick optimization problem. So I'm going to come back to this and start checking into these last remaining questions. If you did not have a question, if you do not have an outstanding question, there are a couple in here. If you do not have an outstanding question, you are welcome to log off. I will hopefully see you next week again. Remember that you can email questions that you would like longer answers to or just reiterated answers to classes@prepmatters.com. And you can look back at these recordings of these sessions as well on the Prep Matters YouTube page. So if you do not have any more outstanding questions, it was great to do calculus with you, and I will hopefully see you again next week. Okay, so I'm going to go backwards first to this mean value. I think it's a mean value question. Because there was a slope of 2 between 3 and 5, there also had to be a derivative of 2 within the same value. Yes, that is what your mean value theorem is saying. If you have a slope of, for instance, in this case, 2, between 2 points, that's your average rate of change. That's the slope of a secant line. The mean value theorem says that if our function is continuous between those 2 points, we will also have a slope of a tangent line equal to that value. At some point, slope of a tangent line, derivative. Yes. Okay, so questions for optimization. Do we assume that minimizing cost is based on surface area? Yes, that yes, for an AP setting, if you're not given more information than that, you can make that assumption. Sometimes they'll tell you more, sometimes they won't. If they don't tell you, that's a fair assumption to make. And no, to our last question here, Eric, you do not need to use both verification ways. It will not, it should not, I should not say will, it should not specify one or the other. You generally have the option to verify in any way that you can or any way that you prefer, as long as you're doing the verification. All right, so it looks like we're good. Again, reminder, you can email questions again if you just want me to reiterate anything that I answered here or said here, or if you want to email in a question that you think of later, classes@prepmatters.com, and I will email you as detailed of an answer as I can. If I don't get any more questions, I will see you all next week.